Okay, so we're onward and upward today with our discussions of pipe flow. All right, and we're going to be, so last time we talked about first defining what we mean by pipe flow and how it differentiates from flow through things that are not pipes. Okay, so pipes are, we're specifically interested in round cross sections. Otherwise, it's what we refer to as a duct. Not really an area of focus of this class, so the theory ends up being pretty similar. And the other thing that differentiates pipe flow from other fluid carrying conduits is the fact that pipes have to be completely filled with the fluid they are carrying, as opposed to open channel flows like spillways, culverts, etc. The reason being that pipe flow can be driven by pressure and or gravity, whereas open channel flows within completely filled conduits rely upon gravity or a slope in order to actually produce fluid flow. So today we're going to move on and really dial down on one of those three flow regimes we introduced, right? Laminar, transitional, and turbulent flow. We're going to be focusing on laminar flow that is fully developed, and kind of loop back around to that derivation we started at the end of last lecture. Kind of finish that out and show how that gives us, for laminar flow, some relationships between things that are of actual engineering interest. Okay? Maximum velocities, flow rates, pressure gradients, wall shear stresses, and then how those relate to head loss, which is something we described when we were doing the energy equation, right? You say between this point and this point, there are 2 meters of head loss in a piping system. That comes from the expenditure of energy to overcome fluid shear stresses in piping systems. So we'll finish up with some expressions for head loss that apply to laminar fully developed flow. So first, we'll aim to relate wall shear stress pressure gradient and flow rate for fully developed laminar flow. We'll use these relationships to calculate how changes in pipe length and diameter affect the flow rate. And finally, we'll calculate head loss, specifically for laminar fully developed flow. Okay, so if today's about laminar flow, right, then the next time we have an instructional lecture, so Monday, we'll be getting into turbulent flow through pipes, fully developed turbulent flow. Something that I actually somehow I managed to completely skip over last time, and my apologies, I don't know, I just missed about an inch in the notes. We discussed this concept, what we call the entrance length, right? Which is the amount of distance that it takes the flow once it enters a pipe or it goes through some sort of change in the pipe. It's the amount of time or distance it takes for the flow to become fully developed. Okay, for the fluid shear stresses and pressure drops to reach equilibrium so that you end up with a velocity profile that does not evolve as you progress down the pipe any further. And so I defined this entrance length, but I didn't give you any expressions for how to calculate it, which was on me. So it turns out that, like most things with pipe flow, okay, the entrance length correlates very well with the Reynolds number. And so dimensional analysis and experiments have shown that the entrance length, LE, over the pipe diameter, okay, is approximately equal to 0.006 times the Reynolds number for laminar flow. And about 4.4 times the Reynolds number to the 1/6 power for turbulent flow. So these are entirely empirical. There is absolutely no theory backing these up, just a lot of experimental data. Some good rules of thumb here, right? So in engineering piping systems, whether it's residential water distribution or what have you, it's very common to find Reynolds numbers that are in the 100,000 to 1 million range, okay, which is way into turbulence. We've left laminar flow in the dust. But at numbers like that, okay, because of this, right, turbulent flow, the Reynolds number is only, or the entrance length is pretty weakly dependent upon the Reynolds number, okay. It's very common then to have entrance lengths. Yeah, it's very common to have entrance lengths that are about 30 to 50 pipe diameters. Okay, if we've got a Reynolds number of 1 million, for example, okay, at 1 million to 1/6 power is going to get 10. So you have the 44 times D for your LCD vacuum. If you had a number of 100,000 for your Reynolds number, then you're going to have about 4.4 pipe length or pipe diameters. So that kind of 30 to 50, though, is a pretty good rule of thumb for most kind of engineering scale problems. So you can use that as kind of a sanity check if you're dealing with turbulent flow and you calculate an entrance length of 500 pipe diameters, then likely your Reynolds number is off by an order of magnitude. Okay, and so let's reinforce this quickly with a quick example. So let's say we were dealing with an HVAC system, so air conditioning, and we're given that to cool a given room. To cool a room, it is necessary to supply 4 cubic feet per second of air through an 8-inch diameter pipe. What is the entrance length on this situation? Okay. We'll go ahead and assume some sort of off-the-shelf properties for air. Okay, we didn't specify an air temperature, which is really what we would need if we wanted to get really exact with this. But we'll go ahead and assume that, right, rho for air is 2.38 times 10 to the negative third slugs per cubic foot. And we'll assume that the dynamic viscosity is 3.74 times 10 to the negative 7th pound force second per foot squared. Okay, so we know that Q is equal to 4 cubic feet per second. And we know that the cross-sectional area of the pipe then is, right, pi d squared over 4, where the diameter is 8 inches or 0.67 feet. So I'll leave this in your hands for just a couple of minutes here to figure out first what the Reynolds number is, decide what flow regime it is in, and then use the correlations I just gave you for entrance length to approximate how long the entrance length will be. Okay, who's got a walk through these inner solutions one at a time? Who's got a cross-sectional area? Yes. All right, let's just about 0.35. We'll just leave it at 0.35 square feet for now. Okay. What about the mean velocity then? Now we know the cross-sectional area. Q is equal to A times U, right? So what do we have for an average velocity? 11.35 feet per second. Good. What does that get us for a Reynolds number? And does that make it laminar or turbulence? Yeah. Okay, 48,000. We'll just leave it at 48,400. Yeah. All right, so laminar, turbulent, turbulence, right? Well over that 4,000 cutoff where we usually elect to call the flow turbulent. So our entrance length to diameter ratio is going to be 4.4 times this Reynolds number calculated to the 1/6 power, right? Which works out to be what? Yeah. Okay, so that's the entrance length. The ratio of entrance length to diameter, though, is going to end up being, your final answer agrees with mine, but it's going to be around 26.7 or so. And so the actual entrance length is going to be 26.7 times the diameter, which will work out to be about 17.8 to 17.9 feet. All right. So, and yeah.
So we're given slugs for density and pound force for dynamic viscosity. Do we not have to convert those to either volts and slugs or volts?
So where that's going to come in is right here, right? So let's go ahead and work this out. So the Reynolds number then is going to be equal to 2.38, right, times 10 to the negative third slugs per foot cubed times 11.35 feet per second times 0.67 feet all over 3.74 times 10 to the negative seventh. And here's where the conversion comes in, right? A pound force is simply one slug times 1 foot per second squared, right? So slug, foot per second squared, okay, times second per foot squared. So here's our pounds force. This is why those slugs aren't often. I mean, people don't like slugs, and I understand it. So it's kind of a weird, archaic unit, but it's convenient because of the fact that you don't need to worry about what do I divide by 1. Do I divide by 32.2 or in fact, when I was teaching this lecture last year, I think I had folks look up the density in the book, and people tended to gravitate towards the pounds mass. And so overwhelmingly, the Reynolds numbers that people came up with were off by a factor of 32.2 because they forgot to divide the density. But if you do the cancellations here, you should find that because we've got a slug here, feet over feet squared, so we end up with 1 over feet. So feet, that the seconds, 1 over seconds, and we end up with no units. Okay, so back to new stuff. So last time we kind of rushed through this derivation, and while the derivation is really short and simple, it's also really important. So we're going to loop back to that, but we're going to generalize it a little bit. So that derivation involved taking the cylindrical chunk of fluid and doing a free body diagram on that to see how the balance of pressure forces and frictional forces worked out in equilibrium. We're going to change it by considering a fluid parcel in an inclined tube now. So we're including the effects of gravity. So we'll draw. I'm going to assume that the flow coming in is fully developed. Oops. This thing will be at some angle theta, horizontal, right? Gravity acts downward, and we're going to consider this cylindrical sort of slug of a fluid that's taken around the center line of this inclined pipe. It'll have a radius of R and a length of L. And we'll set up our coordinate system like so. R and X. Okay. So we're going to use a balance of forces on this red cylindrical parcel to understand how important physical parameters of actual engineering significance interplay. Okay, velocity profiles, we'll get to that in a second. Pressure drop or head loss, flow rate, and shear stress. So the assumptions are, of course, that the flow is steady, okay, and fully developed, which all kind of works out to tell us that that fluid parcel is in equilibrium. There is no local acceleration because it's steady, and there is no convective acceleration because it's fully developed flow. So we can write the free body diagram, or we can draw a free body diagram on this cylinder. Okay. We're interested in the sum of the forces in the x direction, which is along the length of that, or along the axis of this pipe. So this part we did before. Okay, we've got some pressure forces acting on each of the two ends. P times pi r squared, and here P minus delta P pi r squared. In other words, we're assuming that if it flows going that direction, there's got to be more pressure at this end than at that end. Pretty safe assumption. We've got some amount of the fluid's own weight acting, okay, and that would be pi r squared times L times rho g sine of theta. And then acting all along the outside surface, okay, we're going to have fluid friction, which takes the form of tau times 2 pi r times L. Okay, so tau is the shear stress, 2 pi r L is the surface area of the cylindrical outer shell of this fluid element. So, sum of the forces in x, we know has to be equal to 0, so we can write it out. P minus, right, delta P, P minus P plus delta P, there we go. Pi r squared minus tau times 2 pi r squared times L minus pi r squared L rho g sine of theta. Zoom out just a little bit. Equal to 0. Okay, and I'll skip the algebra steps here. And what we'll find is that delta P over L is equal to 2 tau plus rho g sine of theta. This tau ought to be over r. Okay, so here's expression number 1 that we want to keep in mind. Okay, now the interpretation of this is, and I think I've gotten this last time, that delta P, right, which represents the pressure drop over the length L of the element. Okay. In other words, that's the mean pressure gradient. Its job is to overcome the combined effects of shear stress, okay, by tau, and gravitation, the weight of the fluid element. It takes pressure to drive a fluid uphill, and it takes pressure to drive a fluid against resisting friction. Now, if we move this this rho g sine theta over to the left-hand side here, we can write delta P over L minus rho g L sine of theta. Oops, that's what I meant to do. Or L is equal to 2 tau over R. Okay, and this this version is less important for like the intuitive statement it gives, and more important for allowing us to make another assumption about how tau behaves. Right? Note the left-hand side doesn't contain any R's. There's no radius term in there. The left-hand side is dependent upon the pressure drop, the length, the angle of the pipe, and the properties of the fluid inside of it, namely the density. Nothing about radius. So it's completely independent of the value of R. That means that whatever our choice for tau is, okay, however tau varies as a function, 2 tau over R also has to be independent of R. Okay. The only function that can make that happen is if tau is equal to some constant, we won't define it yet, times R. Okay. In other words, what this is saying is that in a pipe flow, okay, we've got our velocity distribution. The shear stress distribution in here has to be 0 at the center line and increase linearly towards the walls of the pipe. Okay? Because R is 0 along the center line. Tau and U. Okay. And if we kind of think about what we know about Newtonian fluids and the way that shear stresses and velocities are related to one another, this should make sense to us, right? We know that where there's no velocity gradient, that we can't have any shear stresses develop because there's no relative motion or friction between fluid particles. Right along the center line, okay, we don't have a velocity gradient, it's symmetric. Okay, so our shear stress disappears. Out here at the walls, where the velocity gradient is largest, we also have the largest shear stress. So this should give us some warm fuzzies. So here we go. So we know that tau is equal to 0 at R is equal to 0. In other words, the pipe center line. And at the wall here, okay, tau is equal to tau W at R is equal to, okay, the pipe diameter. Now this tau W is another term that at this point we've just made up, but we make it up because it's got a special meaning to us, right? All of the friction in the fluid ultimately has to be transferred to the friction of the fluid like next to it. In other words, as shear stress develops at the just off the center line, okay, if you take the next sort of radial slice of fluid outboard of that, it has to exert that friction that's being exerted on it, on the fluid outboard of that, and so on and so forth. And so ultimately, all of that fluid friction is being transferred to the walls of the pipe. And so this tau W is what we refer to as the wall shear stress. And generally, this is what we're most interested in if we're talking about shear stresses. So at this point, if we kind of change our focus and we say we like this tau W, then we can solve for this constant up here, okay, in terms of tau W. right? C is equal to R, or if you prefer, right, 2 tau over diameter. And so if we plug that into our equation for tau, tau is a function of R, right? This now becomes tau W, oops, that should be W, tau W, R over R, or 2 tau W, R over D. So if we compare this with the schematic that we've drawn up there, it matches. All it's saying is that the shear stress, okay, tau, increases from 0 at the center line up to a value of the wall shear stress at the wall. It's pretty intuitive. Okay. Now, if we plug this into, actually, pardon me while I scroll up here a little bit. I want to, here we go. Let's see, which one did I mark here? Okay. I want to star this equation right here, okay, because we're going to keep coming back to this. So if we plug this new expression for tau into this equation up here, okay, that I've starred, what we end up with is delta P, okay, minus rho G sine theta times L, all over L, is equal to, okay, before we said it was 2 tau over R, now plugging in this expression for tau, to 2 tau W over radius. Or 4 tau W over the diameter, okay? The idea is now we have a way of relating the pressure drop over a length of pipe to the fluid properties and the angle of the pipe to the friction at the pipe wall. Okay. This is intuitive now at this point because we can sort of start to see how things we can appreciate, like how frictional, how much resistance there is at the wall of a pipe. You can start to see how that will manifest in terms of the pressure drop required to drive that through the pipe, drive that fluid through the pipe. So if we consider a horizontal pipe, okay, in other words, theta equal to 0, okay, we have that delta P over L is equal to 2 tau W over R. Think back to lab 3, okay, where we had flow through 2 different pipes. Smooth one, rough one. Consider the left-hand side, right? Which one of those pipes had a greater pressure drop per given length? The smooth one or the rough one? I heard of someone mumble rough, okay? So this side is bigger for the rough pipe. Now if we think about this tau W, this represents the amount of frictional stress that occurs at the wall of the pipe. Which one of those pipes would you intuitively think would present more friction, smooth or the rough? Rough, right? More protuberances and rust and stuff generally begets more friction. And so what we're seeing here that basically it's that pressure drop is having to be developed, okay? It's having to expend more of its pressure energy in order to drive the fluid through a more resistible pipe, is what was going on in that lab. Okay, at this point, so this is for a horizontal pipe. All of this, okay, I want to point out, is valid for any fully developed flow laminar, or turbulent. Okay, we haven't made any assumptions yet about the laminarity of the flow. We're going to do that in the next step. But this is something that applies to any flow that is fully developed. Okay, now let's make some assumptions that apply to laminar flow only. For laminar flow, we know, right, that for Newtonian fluid, tau is equal to, right, we said it would be, for two-dimensional flow, we introduced this expression, right, back in chapter 1. We're going to recast this now in radial coordinates. It's mu, dr, du, dr. Okay. Note there's negative sign here we've thrown in there just because we're working in radial coordinates. We want the shear stress to be positive in cases where the velocity is decreasing as r increases, okay, which is the sort of velocity distribution we've hypothesized or seen for this flow. So if we combine this, okay, the equation that we earlier starred, delta P minus rho G sine theta times L over L, okay, is equal to the 2 tau over R. If we plug in this expression for R, or for tau, rather, we end up with a differential equation, okay, that looks like this: du dr is equal to negative delta P plus rho G sine of theta times L over 2L times mu times R. Okay, now I skipped some steps in between here, right, some algebraic manipulations that you can work out on your own if you're so inclined. It's worth noting that what we've done here is we could have gotten to the same differential equation by taking Navier-Stokes and cylindrical coordinates, applying all of the assumptions that we wanted to make, and integrating those. Right? This is like an intermediate step in the Navier-Stokes solution. Why? Because we're talking about the same fluid, same physics apply. Therefore, the same equation is going to fall out in the end. Laminar flow, steady, fully developed. These are all things that come up as assumptions at some point when we're solving Navier-Stokes. So we've short-circuited it, okay, and we've jumped over the actual need to employ the Navier-Stokes equations in their full form. We've gotten straight to this. How would we solve this? We integrate it once and apply one boundary condition. Okay, we only need one because we only got a first-order differential equation. Okay, what boundary condition might we apply? What's going on with the walls of the pipe? We have no slip condition. Right? Velocity is equal to 0. So integrate and apply u equals 0 at r equals r, right, which is the non-slip boundary condition. And we end up with u of r equal to delta p minus rho g sine of theta times L over 4 mu L r squared 1 minus r over r squared. Okay. So now we've got a way to, given a flow where we know the pipe diameter, or therefore radius, okay, the angle of the pipe relative to the horizontal, the pressure drop through the pipe. And the fluid properties, we can actually write out an expression that will give us the velocity distribution. As engineers, we're not usually all that interested in the velocity distribution U of R by itself. You measured it in the pipe flow lab, right, using the pitot tube. But what did you then use it to do? And what quantity did you get from the velocity distribution? You took it and you integrated it, right? Used trapezoid rule to integrate that velocity distribution to get flow rate, which is something that we care a lot more about. So if we integrate we'll get that Q is equal to pi times grad P minus rho GL sine of theta R to the fourth over 8 mu times L. Okay. Now a couple of more substitutions we could make, for example, to get the alternate forms. Example we saw before, right, that delta P minus rho G sine theta L over L, right, was 2 tau W over R, right? That was one of the equations that we came up with. Well, we could take this left-hand side and note that this is buried here in the left-hand side, or the first term in both the expressions for the velocity and the flow rate. We could substitute in its place to get U of R equal to, right, tau W times big R over 2 mu 1 minus R over R squared, or Q equal to pi, let's see, pi tau W R to the fourth over 4 mu so we've got multiple ways of now expressing either the velocity distribution. Okay, if we happen to have wall shear stress and we don't have information on the pressure drop and the angle of the pipe, fine. The wall shear stress will suffice. Same goes for the flow rate. But we've got enough kind of a diversity in the set of equations here that, given either information about the piping system itself or the wall shear stress that results, we could get some useful data out of it. So for horizontal pipes, this leads to a special, okay, once again, for horizontal pipe where theta is equal to 0 degrees, okay, if we took this expression right here, okay, this first expression for Q is going to be equal to pi delta P R to the fourth over 8 mu L, okay, and this simplified version is specifically what's known as Poiseuille's law, okay, and what Poiseuille's law tells us is, oh yeah.
Quick question.
Yes, sir.
R to the third because of like your equation at the top right there. It's over R, so shouldn't that take those? Like that, or shouldn't that take
Let me see here. Yes, actually it will. You're right. Thank you. There. Correct. Okay. So Poiseuille's law gives us a few kind of insights about the way that, kind of broadly speaking, different parameters of the flow interact with one another. For example, it tells us that the flow rate is proportional to the pressure drop. Okay. In other words, for a given length of pipe, you double the pressure drop, you'll double the flow rate through the pipe. The Q is inversely proportional to the length of the pipe. Okay? You have a fixed pump, so therefore a fixed pressure drop, fixed fluid. You lengthen the pipe by a factor of 2, you cut your flow rate in half. Likewise, Q is inversely proportional to the viscosity of the fluid. So you double the viscosity of the fluid, leave everything else constant, you're going to cut your flow rate in half again. And finally, Q is proportional to diameter to the 4th power, okay, or radius to the 4th power, whichever one you're working with. In other words, you double the diameter of a pipe, okay, you don't double the flow rate, you increase it by a factor of 16. It's one of the reasons why something I learned is that if you're going from like a single family home water supply, okay, you might have a 1 or 1.5 inch supply pipe running from the water main. If you're building a multifamily residence, a condo or an apartment complex, people only bump up the pipe size to 2 inches, 2.5, which, you know, kind of at first glance, you think, oh, that's not much of an increase in the capacity. But in reality, you're increasing by doubling the pipe size. You're taking a single family residence and making it sufficient to supply 16 families. So we're going to leave it there. We'll pick up next lecture next Monday with an example that uses this Poiseuille's law, or Poiseuille's law.